Hello, and welcome to my lab report for Lab 4 of Physics 2212, the Circuits Lab. In this report, I'll start with an introduction, where I will discuss the purpose, physics principles, and results of this experiment. I will then go into the actual experiment, where I found the voltage and current in a series, parallel, and RC circuit, along with some calculations in the post-lab. And finally, I will conclude with some closing questions. The purpose of this experiment was to evaluate the effect of resistors in different types of circuits, measure the potential differences across multiple parts of the circuit, and calculate the RC value for a capacitor, which I found to be 6.002 seconds. The physics principles needed in this lab were the loop rule, which states that the potential difference across any loop in a circuit is zero, the node rule, which states that the current going into a node is equal to the current leaving the node, Ohm's law, which gives us the equation to find the potential difference across a resistor, and the equation for capacitance, which gives the potential difference across a capacitor that can then be solved with the capacitor's capacitance. The first circuit I looked at was a basic series circuit with two resistors, one with 100 ohms of resistance and one with 47 ohms of resistance. Using this, the predicted current can be found by dividing the potential difference from the two 1.5 volt batteries and dividing by the total resistance in the circuit, 147 ohms. This came out to be 0.0204 amps, which is what the simulation came out when it was rounded, and this was the same current when the ammeter was reversed. Placing one of the ammeters where the voltmeter measured a potential difference of 3 volts. This is because the voltmeter creates an open circuit with no current. However, the batteries still provide a potential difference at the two ends of the open circuit. I then measured the potential difference at various points of the closed circuit, which, if added up, summed to be 0, which follows the definition from the loop rule. The bottom right shows a graph of the potential difference across the circuit. The point where the potential difference changes is across the two batteries, which is when it increases, and then decreases across the two resistors until it reaches 0, as it completes the loop. Then, I made a parallel circuit by placing a new ammeter parallel to the first resistor, creating an alternate route for the current to travel through. This increased the current at both the ammeters, since the current is now going through the ammeter, which has a 0 resistance instead of the 100 ohm resistor, so the new current would have 3 over 47, or about 0.06 amps. I then had to calculate the resistance of each of the following circuit elements. This was done using Ohm's rule and solving for resistance, giving us that resistance is equal to delta V over the current. These calculations can be shown below. The wire and ammeter in the simulation were ideal, meaning that they had 0 resistance, so the current did not change going through these elements. After creating the RC circuit with a capacitor, I used the simulation to measure the time it takes to charge and discharge a 10 ohm bulb and then a 20 ohm bulb. The 20 ohm bulb took longer to charge and discharge, which is expected as a higher resistance would cause a lower current in the circuit, charging and discharging slower. Along with the total times it took and the voltage measurements from a charged capacitor up to 20 seconds, and then took these measurements to plot the natural log of V over V naught, where V naught is 0.083. which I got from the simulation, and T, which is the time at which the change in voltage is 1 over E of the original voltage, which in my case was 3.31. The slope was negative 1.67, which I got from the graph. Setting this equal to negative 1 over RC and solving for RC gives us that RC for this capacitor was 6.002 seconds. Finally, the first conclusion question asks, what if you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? Well, if we did this in real life, we would not have the ideal ammeter and the wire that this simulation used, so the current would be lowered, which would then change the time measurements of the charging and discharging the capacitor. The second question asked, what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? If we were using a real battery, the battery would have some amount of resistance as the current goes through it. However, the model predicts an instantaneous charging of the capacitor as there is no resistance in the model. This would not happen in real life as there would be some resistance in the wire and the battery, but it would still happen very quickly as the resistance is very low. That is all. Thank you for watching and have a great day.